Welcome back to Core Anesthesia. Whether you are a student prepping for tests and boards or a CRNA here to earn CEUs, we are glad you've joined us. For more about us, make sure to check us out on Instagram at Core Anesthesia and online at coreanesthesia.com.
Welcome back to Core Anesthesia. I'm Cole here with Tanner, and today we want to continue our discussion, part 2, on chemistry and physics. In our previous talk, if you have not listened to that yet, I encourage you to go back and do so. We reviewed the structure of an atom. We talked about different types of bonds and how the interactions form different phases of any type of molecule, which is going to be a solid, a liquid, and a gas. How we convert from one phase to the other, such as boiling point, critical temperature, etc. So if you've not caught that episode, I really encourage you to go back and do so. Today, we want to move into more of the laws of how our gas is going to be delivered into the patient's body from the anesthesia machine, what kind of pressures and temperatures will affect that, and then what are the different types of things that can happen in terms of solubility with different laws of that nature, how things are going to flow, etc. So Tanner, you just want to take us away here with the universal gas law?
This is the equation known as PV equals nRT. In high school, I feel like we always called this PIV-NERT. And if you remembered PIV-NERT, then you would know your universal gas law. So this is your pressure times your volume. This is going to equal the number of moles, that's N, times your constant, which is R, times your temperature. So the number that you use for the constant R depends on what units you're using for the other variables. Typically, we use 0.0821, and then the units we use would be liters, atmospheres for pressures, and then that would be divided by number of moles and Kelvin for temperature. So those would be the variables that we typically use. You should know quickly the conversion. So Kelvin is Celsius plus 273.15. While we're talking about this, just remember that Celsius to go to Fahrenheit is Celsius would equal Fahrenheit minus 32 times 5/9. So those are easy questions that you should know, and might not be the totality of the question, but might be part of the equation that you would need to know to answer questions. That's low-hanging fruit on these tests, and so just remember your conversions there.
I don't know why I'm so bad at knowing Celsius to Fahrenheit. Like I'll get a reading and be like, all right, this is 34.2, and I have no idea what that is.
I have no idea.
Like you would think after years of practice, you'd be able to know, and it's just, for some reason, it's something my brain has never retained.
I know. It's like when I'm actually doing a case, I know kind of like where my zone is, where I'm like, that doesn't feel. I think it's opposite for me. I think when I go to PACU and they're like, they're 96.9, I'm like trying to think into Celsius, like how low are we? Because if we're, like lower than mid 35s, I'm like, that's probably not good. Mm-hmm. But when they tell me that in PACU, I'm like, are you okay with that? I think I'm okay with that. They're not shivering. But also, why is that the first thing that it's like you bring a patient to PACU and you're trying to get oxygen hooked up, and there's like 4 people with thermometers coming at the patient? It's like the first thing that they have to get done anyways.
And then they don't get the right reading. They just keep switching devices. And
I'm like, my SAT is 85. I need some oxygen.
I don't think I've ever seen somebody actually record a low temperature. It's always you just keep checking it until you get a right temperature.
Exactly. Yeah. They like put the end of the thermometer in a bear hugger and they're like, yep, we got it.
Yep.
We're good. Anyways, let's keep on going with the changes here for the different units. So remember that 1 mole of gas is equal to 6.023 times 10 to the 23rd power. I feel like, again, those are just things that you should know. And if you don't know, write them on a flashcard. Again, low-hanging fruit for the test. Why would we use this equation? So we use this equation to determine how a gas will behave if we change any of these variables. Typically, this is something that we're just manipulating one of the variables and then seeing how that changes everything else.
So bear with me here. Going to do a little bit of algebra manipulation. If we have this PIV-NERT equation, PV equals nRT, we rewrite that to bring the T to the other side. So we divide the T and you make it PV over T equals NR. And that's how we get this PV over T part. And if you're going to manipulate any variable of those three, whether it's pressure, volume, or temperature, one of the other two variables has to also be manipulated to keep that ratio the same, because they always are going to equal that NR, and that NR is the moles and the rate, which if we're not changing the amount of the atoms that we have and that rate constant, then that number will always be the same. So really, you can just get rid of that NR and then just make two equations that has PV divided by T equals a new PV divided by T. And that way, whenever you manipulate one of the three variables in that ratio, you're going to be able to figure out what the other variables have to do to keep that ratio the same to equal the other PV over T. Hopefully that makes sense. It's a little bit of algebra, but basically we've derived at PV over T equals a different PV over T, and we can use three different laws that are going to manipulate this equation. And that's Boyle's law, Charles' law, and Gay-Lussac's law. And they take different spins on this equation. So first let's look at Boyle's law. Boyle's law looks at how the pressure and volume are going to change if temperature is held constant. So we're not even going to mess with temperature. So again here, you can basically just get rid of the T in both equations. When you have PV divided by T equals PV divided by T, since that temperature is not changing, just get rid of it. And now we have PV equals PV. And as a result, we just simply know this. If you go up on one of those variables, the other one has to go down. So if you go up on pressure, then the volume will have to decrease to keep that equation equal. And this makes sense. If I shrink a space in a closed container, so if I have a 2-liter container and I shrink it down to 1 liter, all those molecules that were already in there are now going to be under a smaller space. So the pressure inside of there is going to go up, and vice versa. If I take that space and I make it bigger in that container, but I don't change the amount of molecules in there, well, now the pressure is going to be more relaxed in that spot. So I like to think of an elevator. If you're in an elevator with 5 people and all of a sudden that elevator gets half the size, it's going to feel a lot more pressurized in there because you are all crammed together. Whereas if that elevator just doubles in size, you can all spread out and it's going to feel a lot more relaxed, less pressure. So this is an example of Boyle's law. So an example in our body is going to be normal breathing. So we don't change temperature from breath to breath, which is why Boyle's law applies here, because we can eliminate the T from the equation and then just have PV equals PV. And when our diaphragm contracts when we take a breath, it's going to pull the lungs downwards and increase our lung volume. So we're increasing the V in this equation. So based on Boyle's law, this should decrease the pressure inside the lungs, which it does. And as a result, the pressure inside the lungs is now less than the atmospheric pressure. So air from the atmosphere now gets sucked into our lungs, and that's how we take an inhalational breath, and that evens out the pressure. The opposite's true now. When our diaphragm relaxes, it's going to close the volume in that lung. Pressure is now going to go up in the lungs, and so we breathe out that air to exhale.
Since in Boyle's law, you are just taking out the T, then now we're going to talk about different variations of this. So Charles' law is going to assume that the pressure is held constant. So the equation now is going to be VT equals VT. So as one of these variables gets bigger, then the other variable will get bigger in order to keep the same ratio. This makes sense. As something gets warmer and more energy is added in, the faster things move around. So it makes sense that the space the molecules make up is going to be a larger volume if the temperature is higher. So as the temperature increases, then your volume is also going to increase. Gay-Lussac's law is very similar, except instead of like Charles, where you have VT equals VT, it just uses two other variables of Pivner, and this is PT equals PT. And so similarly, where the ratio will increase just like Charles' law, except this is now talking about pressure and temperature instead of talking about volume and temperature. Similarly, though, as the temperature goes up, the molecules are going to move around faster. Since the volume is what is fixed on this, the more energy, the more temperature you add into this, the higher the pressure will go, because those molecules are going to want to spread out and move around, except the volume is fixed. They can't. So the result is that the pressure will increase.
So next, let's move on to Henry's law. Henry's law is the concept that the higher the vapor pressure is, and remember from our first episode, this is the pressure of the gas molecules hovering over the liquid molecules in a closed container. The more gas molecules that are hovering around, the higher the vapor pressure is. So Henry's law says that the higher the vapor pressure is, the more of those gas molecules will get pushed together and convert to a liquid form given that the temperature remains the same. This makes sense in my mind. If you have a closed container and you are adding more and more molecules above the liquid that's filling half the container, and there's all those gas molecules floating around and you keep adding more of them, they're going to start to fill up so much pressure that it's just easier for some of them to convert back to liquid form and fall back down to that liquid level. And this is the idea of Henry's law here. And we often think about this with gases that we deliver through our anesthesia machine in terms of being soluble in the blood. So the blood is going to be the liquid form, if you will, and we're going to deliver these anesthesia gases into the lungs in gaseous form, and then they're going to become soluble and dissolve into the liquid blood that we have. And the higher the partial pressure then of our anesthesia gases, the more of it will become soluble into the liquid. Basically, the concept here is the higher the anesthesia gas concentration we deliver into the lungs, the more of it's going to get transferred into the blood. Temperature can also affect this. As temperature increases, the solubility is going to decrease and vice versa. So AKA, if we have a patient who's febrile, because that temperature now is increased, that solubility is going to decrease and less of the anesthesia gas will become soluble into the bloodstream. On the flip side, then, if you have a patient who is hypothermic and cold, they're going to have more gas become soluble, which means it's going to take longer for them to wake up when you get done because more of it's going to stay in the body and in the blood after we turn off our vaporizer from the anesthesia machine. So this is just another reason why you want to keep your patient at a good temperature. Again, this isn't necessarily the main reason, but this is a plain factor here as to why we want to keep the patient normothermic. It is also good to note here, though, that each type of gas molecule has a different solubility constant. And this is going to be at a specific temperature and pressure. So not all of our anesthesia gases, SIVO, ISO, DES, etc., have the same solubility constant. But with each of these gases, though, they follow the same trend, meaning that they will decrease their solubility as the temperature increases, and they will increase their solubility as the vapor pressure increases.
That leads us into Fick's law. And so, like Cole mentioned, each gas will have their own solubility constants. But what Fick's law talks about is basically talks about the different factors that will influence how the gas travels through to get to the liquid, or how fast that gas gets put into the liquid. So, for example, the larger the molecule, the longer it will take to go through that membrane and move through. That just makes sense, just strictly based on the size. Obviously, conversely, the smaller the molecule, the easier it will be to pass through the membrane. Also, talking about the membrane, this is another factor that Fick's law talks about. So the thicker the membrane, again, this makes perfect sense. The slower the gas will move through that membrane. And then the thinner the membrane is, the faster that will transfer through the membrane. The other thing that you should consider, and Cole mentioned this briefly when talking about Henry's law, is the pressure gradients. So this is another factor that will influence how the gas will transfer through that membrane. So the higher the pressure gradient, the faster the transfer. This makes sense when you think about the idea of diffusion and moving from one side of a membrane to another. We're not typically talking about the speed of transfer. We're just talking about the molecules will go across the membrane to even out the pressure on both sides. But think about if you have a higher pressure on one side of the membrane, it's going to cause a faster transfer across that membrane than if you have a semi-close pressure on both sides, then it's going to be a slower transfer across that membrane. So boil it down. I shouldn't use that word boil. You'll be confused with different laws. To narrow it down, Fick's law will talk about the different factors. Mainly, we're thinking about the size of the molecules, the size of the membrane, and then also your pressure gradients. Poiseuille's law, and I have no idea if I said that right. If you speak French, I assume that's French. You can write us or tell us how you actually say that, but that's what I'm going with. Poiseuille's law is a modification of Ohm's law. So if you remember from physics, Ohm's law is that current equals voltage difference divided by resistance. So when thinking about this in terms of blood flowing through the body, current is going to be the blood flow, and then voltage difference is going to be your pressure gradient, and then resistance is going to be the resistance in the blood vessels, whether that's diameter or if that is obstruction, whatever that is. The resistance is going to be, again, what the blood is encountering as it goes through the blood vessels. So Poiseuille's law more accurately describes blood flow by making the equation that blood flow is equal to 3.14 times the radius of the vessel raised to the fourth power. And that's going to be times the difference in the pressure between the artery and the vein. So that's your pressure gradient. All of that will be divided by 8 times the viscosity of the blood times the length of the vessel. So this is pretty long to keep in mind, but if you go back to the original formula, then you can remember, all of these different factors in terms of what the initial formula looked like. So again, your voltage difference is going to be 3.14 times the radiance of the vessel raised to the fourth power times the difference in pressure between the artery and the vein. And then all of that is going to be divided by your resistance, and your resistance is made up of 8 times the viscosity of the blood times the length of the vessel. You should know this can also be applied to any other fluid that's moving through a tubing. So if you think about pushing drugs through an IV or meds dripping in through an IV, then Poiseuille's law will also describe that as well. We think of viscosity typically as the thickness of the fluid. So the more viscosity something has, the slower it will flow. You can think of this as like syrup or honey having high viscosity, because if you think about if you just turn that container over, it's going to drain out very slowly compared to water. Water would have a very low viscosity. You should know this, that the biggest variable is going to be the radius, because remember, we take the radius to the fourth power. So this will have the biggest play on the outcome of this equation. So if the radius of the blood vessel doubles, then the blood flow will increase by 16 times as long as the other variables are the same. So you should remember that this is going to be the biggest determinant of your blood flow is going to be the radius of your vessels.
And this makes sense in my mind. The biggest thing we do to alter blood pressure and how much is flowing through different blood vessels is going to be your SVR. The more we constrict something, it's going to dramatically decrease the amount of blood flow through that area and increase the pressure and divert blood to different areas. So that just makes sense in my mind. Next, we want to talk about Bernoulli's principle. And this is the idea that the slower the fluid moves through a tube, the more pressure the fluid has on the walls of the tubing. So we like to think of this as if the fluid is moving faster, it's focusing more on moving forward through the tube rather than pushing against the walls and the sides of the tubing. Whereas if that fluid is moving slowly, then it'll try to push out on the walls of the tubing, creating more pressure. So as a result here, if you have a slower moving section of fluid in that tubing, you're going to have a bigger diameter, given that the walls of that tubing are able to constrict and dilate. Whereas if you have very fast velocity going through this tube, then you're going to have a narrower diameter in that tubing. We also have the Venturi effect. And the Venturi effect takes the Bernoulli's principle a step further. And it's the idea that when you have an area of that faster velocity flow, it's going to have that small diameter of that tubing, that constriction that we talked about. And then the pressure, though, is going to be less in this part of the tubing, is what the Venturi effect says. And because the pressure then is less in this part of the tubing, if there's a hole or more of a permeable section of that membrane on that tubing, then any air or liquid on the outside of that tubing can get sucked in through that opening into the tubing from an area of higher pressure to that area of low pressure inside the tubing. So again, let me rephrase that, because that's a lot of wordiness. When you have an area of faster velocity, it's going to cause a smaller diameter on that tubing because there's less pressure pushing on the walls of the tubing there, and more of it's moving forward. So if you have less pressure, then if you have any hole or leak in the membrane, odds are you're going to have higher pressure on the outside, which is going to suck things in. So this concept is how jet ventilation or nebulizers actually work. Are you looking to join an organization where you can work at your full scope of practice? Join Sound Anesthesia's team and benefit from CRNA leadership with over 20 years of experience. Sound CRNAs enjoy career development, a clear leadership pathway, robust well-being resources, and the ability to perform at the top of their license. Sound is dedicated to providing our CRNAs with the tools needed to thrive in their practice. With multiple nationwide opportunities, we are confident you will find the right program for you. Learn more at careers.soundphysicians.com. The next thing I want to talk about is the Coanda effect, and this is based upon the idea that the speed of a gas or a fluid moving through a tubing it's going to be attracted somewhat to the surface of that tubing. And so if the surface of the tubing starts to slightly bend and change direction, the original flow of that fluid will also change direction to stay with the wall of that tubing. So hopefully that makes sense. If you have a tubing moving straight from left to right and the fluid's pumping through there and that tubing curves downward, then instead of that fluid simply banging against the back wall as that tubing curves down, the flow of that fluid will actually curve down with the tubing. And this makes sense for me if you have listened to our talk on babies' circulation differences and the different anatomy in terms of the heart defects and et cetera there. We talk about the idea that deoxygenated versus oxygenated blood flow at different velocities going through the inferior vena cava into the right atrium. And where you have that foramen ovale between the two atriums there, the oxygenated blood has a faster velocity. And so it's going to hug against the surface of the tubing and actually gets diverted through that foramen ovale, whereas the deoxygenated blood doesn't stick as well to that side and get diverted. And so it goes down then into the right ventricle and then out into the pulmonary circuit. And that's one of the ways then that the baby actually separates the oxygenated from deoxygenated blood to bypass the pulmonary circuit and get that oxygenated blood to the systemic circulation faster. So I think that's a perfect example here of this Coanda effect. So I like to think this reminds me of an anaconda snake, and then the curvature of the tubing. I don't know. The curvature of the tubing just reminds me of, a snake has curves and slithers. And so I just remember the Coanda effect is going to be the law that talks about when you have a curvature of a tubing, that the fluid will kind of shift and change towards that side. If that helps you, go with it. If it not, forget I ever said it.
Stick with us. We got all types of. Do you remember my memory one for your nerve damage of the radial nerve?
No. I'm trying to remember. I remember your addition sign, which I thought was the stupidest thing in the world at first, and now I remember it every single time we have a test.
I remember radial is wrist drop because it sounds. I know it's like phonetically it sounds the same, like radial wrist. I know it's spelled very differently, but
I don't remember that. Did we talk about that in an episode?
Yeah, we were all turned around backwards, but anyways, I will not forget that now. Anaconda and Coanda effect, the curvature of the tube.
I always remember you said for the vocal cord muscles, in terms of what adducts and abducts.
Yeah.
You said the lateral.
The lateral cricoarytenoid.
You put your hands out laterally to make a plus sign, so that adducts.
Adducts.
Even though adduct actually means to bring closer to the midline.
Yeah.
So it's kind of the opposite. But now I always remember, like every time I remember that now,
Yeah.
you just standing in front of the classroom with a big cross saying lateral cricoarytenoids.
I don't know why jumping through 17 hoops to get to the final answer makes it more memorable in our minds than just remembering the stupid thing in the first place. But
it works.
This is my lot in life. This is how I have to remember things. All right. The next thing that we'll talk about is Reynolds number. Reynolds number is basically just the formula that will describe the flow of something. So the density times the diameter times the velocity divided by the viscosity. And what you should know about this is if Reynolds number is less than 2000, it's going to be considered laminar flow. So this is where the molecules are moving in sync in parallel fashion through the tube. If it's above 4,000, this would be a faster movement through the tube. Then this would be considered turbulent flow. When you think of turbulent, don't think of like a nice, smooth parallel flow, but think of things flowing in different directions, increased speed and pace. So this is going to be a Reynolds number of greater than 4,000. So typically, this turbulent flow is where we'll see the direction or diameter of the tube changing. The other thing that we want to mention is transitional flow. So this is going to be in between laminar and turbulent. So that's between the 2000 and 4000 Reynolds number. That will be considered transitional flow. One other key point that you should know, and I feel like this comes up on every test, is that laminar flow is going to be more dependent on the viscosity, where your turbulent flow is going to be more dependent on the density. So going back to the initial equation, density times diameter times velocity divided by viscosity, those are the variables that we're talking about. But laminar flow is going to be changed more based on the viscosity. So that's going to be what everything is divided by. Turbulent flow is going to be mostly dependent on the density. Again, that's one of the variables on the top of that equation. Dalton's law, this is something that we talk about often in anesthesia. So we often are dealing with multiple gases and the atmosphere that we're breathing. We talk about pressure. So we talk about the atmospheric pressure at sea level compared to the pressure at varying altitudes. Pressure is going to be made up of all the atoms, molecules in a space. So while we can't see the molecules in gaseous form, they are there filling up the space and creating this pressure that we consider atmospheric pressure. Dalton's law is that if you add together all of the partial pressures of each of the gases in a container, then you'll get the total pressure for that container. To me, I wish every law was this simple or made this much sense in my mind, but basically every different type of atom that is making a gas in a container, when you're adding all of those partial pressures together, then you get a total pressure for the entire container. This is all that Dalton's law is saying. We'll just do a quick example. If the total pressure in a container is like 500 millimeters of mercury, and there are three types of molecules making up the mixture, the first one is 125, second one is 300, then you can figure out the pressure of the third molecule. So you would just add 125 to 300, and that would give you 425. You would subtract that from your total pressure, which is 500. We said that was the total pressure in the container. So that means that the third gas, the third molecule, is going to be 75 millimeters of mercury. Another example would be at sea level, the total atmospheric pressure is 760 millimeters of mercury. So all of the molecules or atoms that are in the air will add up to this total of 760. We know that the air that we're breathing is 21% oxygen. So we can use Dalton's law to figure out the partial pressure of oxygen. We would just take the 760, which is the total. We multiply that by 0.21. That's the percentage of oxygen. And we know that the amount of pressure that oxygen is making up in the air that we're breathing is 160 millimeters of mercury at sea level. So that's just 0.21 times that 760.
Another good example of Dalton's law is, especially in anesthesia, is going to be our vaporizer. And we dial the anesthesia gases to a certain percentage. So let's take desferrine, for example. A full MAC of that, we're trying to get the expired value to be around 6% when we dial this on our anesthesia machine. At sea level, we calculate this based on 760 millimeters of mercury, as Tanner talked about, and you take that number and you multiply that by 6%, so 0.06, and you get approximately 45 or 46 millimeters of mercury. However, at higher elevation, the total pressure of the atmosphere may only be 700 millimeters of mercury, depending on how highly elevated you are. And if we take 700 then times your 0.06, you only get 42 millimeters of mercury. So in this case, if we dial the same on the vaporizer to try to get that 6%, at this elevation, we actually would be giving the patient almost 4 millimeters of mercury less of desferrine than at sea level. And again, this may not be significant enough, or it may be significant enough to under anesthetize your patient and you're going to make them light. And while some vaporizers do account for this difference in atmospheric pressures and they will alter themselves so that you don't have to worry about dialing a different amount, some do not. And so I encourage you to go listen to our inhalational anesthesia talk for more information on this topic. We kind of go through how this process works and what would be the difference of dialing something at sea level versus in Denver, and what vaporizers would change that, etc. The last law we want to talk about is the law of Laplace. So for a sphere, it says that tension equals pressure times the radius divided by 2. And again, this is for a ball or a sphere. And pressure then here is going to be the force pushing against the walls of the sphere, and the tension is going to be the force trying to pull apart the sphere. So think of two people grabbing your arms and your legs and trying to stretch your body out. And this is going to be tension put on your body. It's a pulling force trying to pull the actual cells of your body apart. Pressure against the walls of the sphere, they're going to be coming from both the inside and the outside. But however, for this equation, we're really mainly concerned about the pressure from the inside trying to push those membrane cells lining that outward and make that sphere bigger. So examples of spheres in our body that we can apply the law of Laplace. The one that I think everybody automatically goes to is alveoli, and then also the chambers of the heart. And so when specifically talking about the ventricles of the heart, we can manipulate the law of Laplace to become tension equals pressure times your radius divided by parentheses your wall thickness times 2. Based on this equation, the thicker the walls of the ventricle, the less tension there'll be on that chamber. This makes sense as to why if we start to have high afterloads, chronic hypertension, etc., that are going to put more stress on the heart, the ventricle walls themselves actually become thicker and form hypertrophy in order to decrease the amount of tension then that there's going to be on the actual lining of those ventricular walls.
The last thing that we want to talk about, and you heard me correctly, this is the last thing in the talk. You made it. Is lasers. you did it.
I'm not gonna lie. More excited that we're gonna.
Yeah, for sure. I'm not gonna lie. Sometimes on these types of episodes, if I'm reviewing them in the car, I need to take a break like halfway through and listen to a couple songs or take a break because it's stuff you have to know, but it's not exactly the most riveting thing to listen to for hours on end.
I think this is going to be one of the episodes that I like listen to 2 days before I take boards, just as a last minute throw this in the front of my brain, and then I'll probably forget most of it.
Yeah,
when I walk out of the test. I mean, I'm going to actually remember this every day to take care of my patients.
You need to know this for every anesthetic you give, obviously, but in case you don't.
That EGD, got to know how.
All right. So the last thing, lasers. This stands for light amplification by stimulated emission of radiation, which raise your hand if you didn't know that lasers was an acronym. My hand's raised. I thought it was just like what we called those things. Did you know that? Maybe. You probably knew that.
I kind of, yeah. I would not have been able to tell you that's what it stood for if you asked me, but I knew it was light amplification. I knew that part.
Nah, I thought it was just like an English word we use to describe a red thing that, had no idea. Anyways, remember on the last episode, we talked about electrons that are going around in an atom that occupy different shells and rings. So if those electrons get energized, they can momentarily move to a higher ring and release a photon, and then it will go back to the original orbit. So this is called spontaneous emission. This is what we're talking about, the photon they're being released. If the electrons are continually energized in this higher ring, then all the photons being released can be released in the same direction. This is called a stimulated emission. So this is basically what the laser is. So lasers can cause fires or burns. These are some things that we need to know about in the operating room. So we need to take some measures to protect both ourselves and the patients with proper shields, especially goggles is the main thing that we want to think about. We also want to think about what can happen with your airway. So remember that the endotracheal tube could also catch fire. So you try to use a laser ET tube that is going to be resistant to these lasers and would not provide more fuel for the fire. You should know that the cuff is still a potential fire hazard. So even on these laser resistant ET tubes, you should know that the cuff is still something that can cause a potential fire. So we often fill the cuff with saline or we use methylene dye. So then if they do cut the cuff, then you would be able to see that very easily that the cuff is cut. If a fire does happen, then you're going to want to immediately stop all gas flow. You're going to extubate the patient, make sure you do not use positive pressure. If you give positive pressure, that is just going to cause more oxygen there to go through, more fuel. So having a blowtorch in the OR is considered very poor form. So it's something that you should avoid as you extubate this patient. Go ahead and extinguish the fire with saline. You can mask ventilate the patient. And then this is where you need to determine next steps. So do we need to reintubate? Are there burning fragments that fell into the airway? We need to do a bronch, lavage. This is kind of the next steps that you need to consider. But the main thing you want to do is just get the source of the fire out. So you want to, again, stop your gases, extubate, and make sure you're not potentiating any problems there with the burns.
I can just imagine, the patient starts at the fire and the thing you want to do is quick take the tube out and you're just trained, crank up your APL valve and squeeze the bag and just vroom. I can just picture a huge blowtorch coming out.
After, of course, you've like untaped
fire.
the eyes, you let down your pilot balloon, you crank up your APL, all your steps for a normal extubation. You probably
George, take a deep breath for me.
Tap him on the forehead, and then light up the whole OR with this positive pressure. Don't.
It sounds so stupid to say don't do that, but like I could just see,
for sure.
You're just what you do when you extubate somebody. You just turn the APL valve up and.
Yeah, I think of that all the time when people tell me like, stories from back when they were in school. You wouldn't believe so and so did this, and I'm like, man, I would probably do that. There's a day that I would probably do that.
Mm-hmm.
Like every horror story you hear, you're like, man,
that could have been me.
That could have been me for sure.
At the same time, though, I don't want you to think that we always put pressure when we extubate. I like to also suck out. I just learned this week actually to put your Yankar into the ET tube as you pull it out instead of providing positive pressure, and it just sucks out all the gunk. Because in my mind, you squeeze the bag and it just pushes the gunk down into the cords as you pull the thing out.
Mm-hmm.
So I've always kind of been wishy-washy on it. Sometimes I do it, sometimes I don't. But a CRNA showed me that this week actually. You just stick the Yankar into the tube at the very last second as you already deflated the cup and you're going to pull, and it just like sucks everything out. And I have gotten so much gunk to come up out of that tube as I'm pulling it out. It is unbelievable, which makes more sense in my mind than squeezing the bag. I've tried it 3 times in a row the last 3 days. They were all smoking patients that had just a bunch of in there. But it is so satisfying to see all that stuff come up in the tube.
Yeah.
That was in their mouth.
For sure.
On that note, this wraps up our part 2 of chemistry and physics. If you stuck with us through the end, go get yourself an ice cream or something because you deserve it.
You deserve it.
A double scoop. So hopefully this has been helpful just to get us more prepared for boards. And if you can, try to take some practical uses out of this for your practice.